Hello everyone, my name is Rehema Moado from the Sokoine University of Agriculture, and I'll be with you as an instructor in this course, Machine Vision in Agriculture, YEESI 104 according to the curriculum, and take you through this part of the introduction of the course, and we'll see what this course is all about, the course contents, and the introduction part of the images, because it's machine vision. So it will start also introducing some of the basic parts of this lesson. So the first thing I want you to understand what this course is all about, which this course wants students to develop understanding on how robots and computers sense and recognize the surrounding agricultural environment. Because it's machine vision in agriculture means that we need to understand how these computers or robots are used to recognize the things that surrounds them. And at the end of the course, the expectations is that each student should have demonstrate knowledge on arithmetic and logical operations on images, and also develop systems that can recognize objects, and demonstrate also understanding of basics of visual learning and how neural networks perform classification tasks or object detection. And also we'll look at some examples where we'll deal with image processing and manipulation by using common libraries and tools, as well as common hardware, such as the Raspberry Pi. So I believe that this will be an interesting lesson, and it also makes students competent and comfortable when you're dealing with many different examples, as well as participate in communities challenges such as the Zindi challenges, and also such as cargo. So I believe that this will be an introduction that gives you the basics, and also at the end of the lesson, each student should be able to do many examples from the beginner level, as well as more advanced examples. So this course has a lot of contents, but specifically we'll deal with the basics of image processing. Then we'll also deal with object recognition, different algorithms that are used in object recognition, as well as networks and frameworks, such as the convolutional neural network mode. And we'll also deal with common examples that will make you gain more concepts and understand different concepts, such as number plate recognition, which is a common examples using deep learning neural networks, as well as another example such as face detection and recognition with the deep neural networks. Also, after this, we'll also see now examples that are common to agriculture, such as crop disease detection and classification, or crop pest. So at the end of the lesson, if you work on these examples, the technical part now or the practical part, you will be very competent in dealing with many other examples or advanced examples. So we begin our lesson with introducing what really is machine vision. So when somebody talks about machine vision, he or she only refers to the technologies and methods that are used to extract information from an image on an automated basis. And with machine vision, because it deals with images, you need to understand the use of a camera to get an image, the computer vision algorithms that help you to process your data, interpret your data, and extract information from that data that can be used now to instruct other parts of the system to act upon such kind of a data. For instance, now you're talking about robots. If a robot is used to maybe harvest, meaning that they harvest a crop, or let's say like harvest fruits such as oranges, you need to train your robot to understand, okay, these are leaves, this is a tree, this is an orange. And from that data, it should know that, okay, after knowing that this is an orange, what should I do? I'll either pluck it from the tree and feed it into another part of the system. So this is all about machine vision. You'll know how a system can do all that, and the underlying algorithm that makes a system able to do such operations. So machine vision in agriculture is very important because it has a lot of applications. There are many applications, but here I'll list just some of the few common applications of machine vision systems in agriculture. The most common one is the use of field robots. Now, field robots, they're used either in harvesting or planting or weeding. You'd see machine vision systems that are used to categorize crops and provide visual input for all the tasks that are listed above, like harvesting, which is common. So I've included an example of a cotton picking robot, and it's a YouTube video that you'd see how a machine vision system is used to support in harvesting. Instead of a human being to do all that work, that tedious work, a robot now is used to do that. So you can see applications of machine vision, how it's important in simplifying the work that mostly human beings are used to doing. Another example is that a machine vision system can be used in either counting or sorting or grading. We've seen these crops such as horticultural crops that easily can go bad when they're in storage. So a machine vision system can be used to sort which crops are either good for shipment or bad that should be discarded. Or another type is that a machine vision system can also be used in counting. If you have so many like fruits or oranges or mangoes or what, you want to count them. So a machine vision system can be used to detect where object recognition, like, okay, this is an orange, and count how many oranges are there. So it's really important because as the work is really tedious, you can't just count like hundreds of oranges as a human being. Is tedious. So with machine vision system, you can really simplify your work and perform these operations by using a machine. So I've also included an example, which is a YouTube video that shows you how a machine vision system can be used to count fruits. And for this case, it is oranges. And then another application, now we've talked about the crop side, let's talk about the livestock part. As you know, agriculture includes both the livestock part and the crop part. So with livestock, a machine vision system can be used to monitor the growth of livestock, such as cattle, and also can be used and identify certain diseases that are common to cattle, like a disease. It can be used to know which type of the disease that the livestock is affected by. So I've also included an example that shows how a machine vision system can be used to identify cattle. There are many examples. Another example which now is gaining recognition, that is assisting genomic prediction, like predicting the best parents that can use to increase the yield, crop yield. For instance, choosing the best parents that are maybe resistant to diseases or pests. Identifying which phenotypic characteristics that are the best to assist in to increase the yield of crops such as maize or other cereal crops. So these are just some of the few examples that I've highlighted. There are many applications, but these are the most common ones that I wanted you to be familiar and see how this module will help you develop such systems. So now I want to talk about the pipeline. As we have seen what machine vision system is all about and some of the most common applications, we come to development part. The development part needs you to understand the pipeline, which gives you the steps and process that is taken from how you input your data to how you get the output. So it includes all the necessary steps and processes that are used to analyze the image data, how you're going to process it and analyze it, and finally making prediction based on the data that you feed into your system. So the pipeline now. The pipeline includes the input data, the part that takes the input data, which for our case, it's images and videos. And videos are just sequences of images. Then after getting the images into your system, you need to pre-process it. Now pre-process them. So pre-processing part means that either you clean your, in machine learning, the image pre-processing part is either you clean your data if they're missing images, or you standardize the images according to what your model requires, color transformation, and also resizing, cropping. So there are many, many operations that we're going to talk about when you talk about pre-processing, because this is the part that really defines how the accuracy of your model in prediction accuracy or object detection accuracy. So this is the part that we'll spend a lot of time, because it really determines the accuracy of your model. Then we'll talk about feature extraction, where you find the distinguishing characteristics of each image. If you are talking about a human being, let's say face recognition, how are you going to distinguish the eyes, the nose, the mouth, the ears? So those are the distinguishing characteristics for a system to know, okay, fine, this is a face. After doing the correct feature extraction is when you go to the model development stages, where we'll talk about different models, mostly convolutional neural network models. Here I'll also introduce you to various frameworks that are commonly used for you to help you in development. And we'll talk about how you're going to determine the model accuracy, how you're going to optimize your model. So we'll talk about a lot of things, but I really want you to focus on what you feed into your model. You know, every picture tells a story, and the garbage in, garbage out. So if you don't use the correct images, your model will have a lot of false positives. We'll see what are false positives later on, what are true negatives, and so on when you are dealing with model performance. So you really need to be very careful when it comes to the pre-processing part and the feature extraction part. So now this is an example, the example that tells you what really the pipeline is, because now when you are developing, you really need to understand what your pipeline is. That it gives you like the direction, like where you're going. So this is an example that you have an input image, which is a motorcycle for this case. Now the motorcycle, you feed it into your image. You start, you start pre-processing it before feeding it into your model, and you do a lot of geometric transformation, enhancing the images, resizing. You do data argumentation. We'll see what data argumentation is. If you have a small data set, and we know deep learning algorithm are data hungry, so you need to understand how you're going to do different transformations that you do to increase the training size of your images of your model. That the training set has to be really big for your deep learning algorithm to be robust. Meaning that if you're giving an image today, it's black and white, you need to give more examples, more training examples, so that your image, if gets another test example that is not either left or right, or a certain degree of rotation. So you need to have a lot of transformations for your model to be robust. Then we'll do feature extractions, like I say, finding distinguishing characteristics of that image. Like for instance, for this is a motorcycle, you need to find distinguishing characteristics. If you're classifying it with, if you are given examples such as dogs, cats, and cows, you need to classify and tell like, okay, this image is really a motorcycle to some degree of accuracy. So you need to find distinguishing characteristics of that image, which are, for instance, for a case, you see tires or a seat or many, many distinguishing characteristics that distinguishes it from either a dog or a car, as this example. After that is when you go to the model development stage. You'll choose different type of models. You'll see a selection of the model to use. And for this case, it's a classifier that has 3 classes, and it's either a motorcycle, it's a car, or it's a dog. And you see that the model classified that this is a motorcycle to an accuracy of 85%. So that's the pipeline, and that tells you from the input to the output stage. And you can see how you're going to increase the accuracy for your model to be more confident that, okay, fine, this is really a motorcycle to maybe 99.9%. So this is an image, and I've included the source where I got the image. And this is a good example to show you that you need to understand all these steps before starting developing your models. And now, before I proceed now to discuss each part of the pipeline, I really need to ask you this question. I really need to get your thoughts. You can put your thoughts in the comments. Can a machine vision system achieve better performance than a human brain? So I really want to get your views. What do you think? Do you think that a machine vision system can really be better in terms of performance than the human brain or not? So it's an open question. I really need to get your views on this. So let's move now to the first part of the pipeline, which is the input data. Now, we say that machine vision system is all about images. So we need to understand what is an image and how is it interpreted in a computer system. So in a computer system and machine vision application, we deal with images, like I said, or video data. For our case, video data is a sequence of images. So an image is a matrix of picture elements or pixels that we'll see how a picture element is when it comes to a digital image. And it's represented with a two-dimensional array of numbers, which are the picture elements, ranging from 0 to 255. 0 means black and 255 for white. So that range of images, the picture elements that range from 0 to 255. And then it's also represented by a mathematical function f of x and y, where x represents the horizontal pixels and y represents the vertical coordinates. The value of x and y at any point gives you the value of the pixel at that point, and also it gives you the intensity of light that falls into that point of the image. So you really need to understand that a digital image in a computer is represented by a mathematical function f of x and y, and the value of x and y at a certain point gives you the value of that pixel at that point, which is the intensity of light that falls into that part of the image. So this is really important when you're dealing with inputs to your model, because you need to sometimes resize your model according to the requirements of the model. Some models require that the size of the image to be changed to fit like 64 by 64 or 25. There are so many. So see how you're going to resize your model. How you're going to resize your images to fit into the model that you're using. So like I said, for our case, we see our images. What we see in our naked eyes, what we see is an image like this. This is an image of a maize plant that is affected by fall armyworms. Credits to SUA. This is an image I got from the SUA website, which shows how this harmful pest, the fall armyworm, can damage maize crops. So this is what we see. But if we keep it in a computer, this is what a computer sees: a set of pixels, which are the picture elements that represents the intensity of light that falls into that image. And then there's different classes of image. Because we're dealing with images, like I said, we'll deal with different types of images or classes of images. Now, a model can take colored images. The colored images include all the color information for each pixel. So for this case, for instance, on the left-hand side, this is the color image. It has all the information, all the pixel values. Like you could see green, you could see pink, you could see yellow. So it gives all the color information for each pixel in that image. Now, on the other hand, the grayscale image consists of shades of gray. And you'll see where we can use colored images and where we'd opt to use grayscale images. Normally, grayscale images are computationally efficient, meaning that they don't consume a lot of your computational power. It's easier to process just these shades of gray than processing the whole color information of each pixel. So depending on what the application, what you're doing, you'd see where to use color image and where to use grayscale images. For instance, if you're doing edge detection, most of the time you'd change your color image into a grayscale image. So it's easy to work with grayscale images. So there are many applications, again, depending on what you want to get as an output. You choose the choice of image to use, the nature of the images to use. Also, another class of image is the binary image, which is a mostly black and white. You could see this is an original image of a banana, which has white, yellow, green, different colors, but you convert it into a binary image of white and black. So white, like I said, 255 and 0 for black. We will also see how applications that you would use colored images and applications that you can use binary images, and how to convert a a colored image into a binary image. Another class of image is called multispectral images, which capture data ranging across the electromagnetic spectrum. I believe we all know the electromagnetic spectrum, and which has, visible light, the visible light that the light our naked eyes can see. And then we have the part where it has the ultraviolet, we have the part where infrared light. And you need to revisit that to understand the electromagnetic spectrum. But for our case, because we're focusing with the digital images, just the colored image, which is in the visible spectrum. Now, for multispectral images, if you're talking about multispectral images, means that for a certain specific wavelength. A common example is the applications in remote sensing, where you could use hyperspectral images to either mark your fields. You see drones or satellite images, especially drones that have these hyperspectral cameras that can classify your field depending on the light reflected from these hyperspectral cameras. And nowadays, hyperspectral images are gaining a lot of recognition. For instance, there's this application which I really like. Normally, if you're talking about crop diseases, you'd notice the crop disease when it's, for instance, maybe a disease that affects the maize leaf. You'd notice the disease when it appears on the maize leaf. But with hyperspectral cameras, you could notice, you could even predict before it starts appearing on the maize leaf, because these cameras extract really good information of they are powerful beyond what our naked eyes can see. So it's a really fascinating application, and we'll see if we can get examples and deal with hyperspectral images later within our class. So for today, this marks the end. We have talked about what machine vision, we have introduced what machine vision is, and we have seen different applications. There are many applications, but I have highlighted the common applications. And we have seen the pipeline, which you need to focus when you're developing your models, the correct pipeline to follow to get the most accurate results. And then we have seen the classes of images that we'll use, the type of images that we use when you're developing our models. So for today, let's end here. And the next part, we will talk about how we are going to handle images, the basics of handling different types of images, how you're going to read an image or read many images. So we're starting the practical part, which is the most interesting part. And I really welcome you all. And I hope that at the end of the course, everybody is going to really be confident and comfortable in doing these machine vision examples. So thank you for today, and I welcome you all to the next lesson. Thanks.